My name's James Newton King. I'm an engineer on the .NET team, and today I'm going to be talking about gRPC, a high-performance technology for communicating between apps and services. So let's talk about what gRPC is for anyone who's not familiar with it. It is a popular open-source remote procedure call framework. Remote procedure call frameworks make it easy for apps to talk to each other. There are alternative RPC frameworks out there, for example, Thrift, but we've observed that the developer community is really unifying behind gRPC as its RPC framework of choice. gRPC is run by the Cloud Native Computing Foundation, and Microsoft has been working on an implementation of gRPC for .NET that we have contributed to the Cloud Native Computing Foundation. gRPC is not new. It was open sourced in 2015, but it's built with modern technologies. It's a union of HTTP2 and protobuf. We'll talk more about the benefits of those technologies throughout this talk. gRPC is designed for modern apps, particularly microservices. It is very high performance and it is platform independent. You can think of gRPC as not one application, but it's more of a standard. It's a standard way of talking between computers. And then there are implementations of gRPC for different platforms, and all of them are interoperable with each other. So if you are building a .NET app and you want to talk to a gRPC service in Go or Node or Java, C++, Ruby, Python, pretty much every popular language has a gRPC implementation available today. Let's go into protobuf. In gRPC, protobuf serves three purposes. The first is it defines a language-independent way of declaring protobuf messages. Protobuf is a contract-first serialization format. So we can see here on the right, we have a basic protobuf declaration of a couple of messages. These are typically stored in a proto file. So here we have a subscribe request, which has a topic property of type string. Then we have an event with ID and details. This is a language-independent way of declaring messages. In protobuf, you can give this to different languages and they're all able to use it. This proto file was also used to define a service model. So the service is like the structure of the calls that people are able to make to a service. So here we can see we've got a topic service, which has a subscribe method. You can think of a service in gRPC like a controller in MVC and a method like an action. And finally, protobuf is the actual wire format. So when we're sending data between our gRPC services, gRPC will take our .NET objects and it will automatically serialize them into this binary format and send it across the wire. So interestingly, with protobuf, it is a binary serialization format compared to text-based formats like JSON or XML. There's pros and cons of this. A pro is it's very fast. Computers are good at reading and writing binary, and also it's very small. A con is you can't easily read it. So you need tooling and that contract file to be able to understand a protobuf message. So I think .NET developers, we're all familiar with building HTTP APIs, aka REST. So I want to talk about some of the underlying differences between remote procedure calls and HTTP APIs. So gRPC, it's an opinionated contract-first RPC framework. That proto file is really at the heart of a gRPC service. Meanwhile, HTTP APIs, typically the first thing you would start doing is you would start writing code to generate URLs, so setting up routing, worrying about HTTP methods and JSON. You think about the content first. And although you can create a contract for HTTP APIs, you might have heard of OpenAPI and generating one with Swashbuckle and .NET. That's like an optional step, while it's very much required with gRPC. With gRPC, the contract and that proto file is designed for humans to read and write. And this is important because the actual content is binary. So the proto file gives you a way to easily understand what you're sending and receiving. Meanwhile, with REST, the content is for humans. So you can look at an HTTP 1.1 message. It's all just based in text. You can look at JSON. It's also text. You're very easily able to read it and understand it. So that's good for debugging, but perhaps not so good for performance. And finally, gRPC, it hides the complexity of remoting. So that proto file is used to drive code generation. So we're able to generate a service base class on the server, and it will wire up all the routing and serialization logic for you, so you don't need to worry about it. And even better, it will generate a strongly typed client for you to call and invoke your RPC methods as if they were a regular .NET method, and then you just await the result. Meanwhile, REST, it emphasizes HTTP. So you're constantly thinking about URL routes, your structure of your JSON, and in the client, you're probably building up an HTTP request manually, although you can integrate with Swashbuckle and code generation and perhaps do it for you, but it is an optional step. So if I was going to sum up these two approaches, gRPC, it focuses on performance and developer productivity, while REST has the widest audience. Like everyone can do HTTP 1.1, everyone can do JSON, and it's very easy to get started with REST. There's no code generation involved. So with that, let's do a demo of building our first gRPC service. So I'm going to launch Visual Studio, and we're going to choose to create a new project. Now, starting with .NET Core 3, we ship a basic template for gRPC. So we can type gRPC into our search bar, and a gRPC service comes up. We'll click Next, we'll click Create, and what we're doing here is we're going to create a basic Hello World app. It has a greeter service, which we send a name to, and then it will respond with a message containing our name. Okay, so now we have Visual Studio has set up our project. Let's take a look at the files we have. We've got our standard ASP.NET file, so we've got a startup file, we've got a program CS, we've got settings. We've got a couple of new files which you might not be familiar with. So we've got a protos folder. So this contains our proto contract, which we talked about. Here we've got our greeter service, which has a say hello method. We've got a hello request, which we take a name property, hello reply, which returns a message. Then in our services folder, we've got greeter service. So greeter service is our implementation of that contract on the server. So we override the say hello method. We're taking our hello request message. We're returning hello reply. And then within the actual body of a method, we're taking the name and we're setting it to the message. So we're saying hello to whoever called our service. So something which might jump out to you straight away is, where have these types come from? These are the only files we have in our application. Where has hello request, hello reply, and greeter base come from? So I talked a bit about code generation before. Code generation is really at the heart of gRPC. So tooling is able to look at this proto file, parse it, and generate files to allow us to very easily use and create gRPC services. So it's able to see we've got a greeter service, or generate a service base type, and it will generate basic DTOs for these two messages. And the way it knows to do that is there is this protobuf element in our project file. We're saying here is a protobuf file, and we want to generate a server base type because we're on the server. We specify server here, and then it will just automatically happen for us. And we can see this in action if we F12 into our message. We can see we've got our hello request, and we've got a message up here saying it was auto-generated for us. Although this is code generation, I wouldn't be afraid of it. I think there's good code generation and bad code generation. The bad type is stuff which you need to manually generate yourself. You need to check it into source control. You need to worry about people going in and modifying it and making it out of date. Meanwhile, good code generation, it all happens for you. Visual Studio and .NET will just ensure that any code generation is continuously up to date. as soon as we modify this proto file, it will be updated. We never need to check it into source control. Okay, so that's our service all set up. Let's create a client, because we need to create a strongly typed client to talk to our service. To do that, we'll just create a basic .NET app. In this case, we'll just create a console app. We'll click Next and Create. I'm running some preview SDKs on my computer, so I'm going to use 3.1. Let me just compile everything to make sure everything's working. Okay, so that worked. So the first thing we need to do is we need to add our proto file to our console app, because both sides need to know about that proto file. To do that, there are a couple of different ways, but the fastest way in Visual Studio and Visual Studio for Mac is there's this Add Connected Service option when you right-click on dependencies. Once we click on that, we have an option to add a service reference. Anyone who's done WCF, this might look a little familiar, except instead of pointing to some WSDL, we're going to be pointing to a proto file. So we'll select gRPC in here, we'll click Next, and then we're going to browse on disk to our gRPC service, and we'll choose our proto file, click Open, and then here we have an option to say what kind of code generation do we want. Because we're in a client, we'll choose Client. And that will generate a strongly typed client for us to call our gRPC service. So a bunch of things are happening now. Basically, all that's happening is some NuGet packages are being added to our CSproj file, and then the proto file is also being added. So here are our NuGet packages. So Google.protobuf, that's a serialization library. This is the client gRPC tools. This is the tooling, and then our actual proto file. And the only difference here is we're specifying client instead of server. So now that we've done that, let's go ahead and call our gRPC service. So first thing we're going to do is we're going to create a channel. So you can think of a channel, a gRPC channel, as like a representation of our connection from the client to the server. In this case, we're specifying our address of our local server. We're creating our channel, and then we want to create our client using that channel. So our client is a strongly typed representation of that greeter service, except instead of a service space, it's a client to call it. And if we F12 into this, again, we'll see lots of generated code that was all done for us. Now to call our service, and this is very easy. We simply invoke a method. So we're calling client.sayHelloAsync. Because it's async, I'll need to make this method async. And we're passing in our request. So like we had hello request on the server, we're also generating hello request on the client. We specify a name and we await the result. So an RPC tries to abstract as much as possible all the underlying mechanism of serialization and URLs and routing. The client does all of that for us. We're just able to invoke it as a method like it was a method within our local application. And finally, let's just write out to the console our result. So we should be good to go. Let me bring up our console, and we will call our console app and our gRPC service. So gRPC service 34, and we'll .NET run it. And then over on our client, console app 56. And if all has gone to plan, oh, we've got a bug here. Let me just compile to make sure everything's working. Give me one moment. Why is this not working? All right, we seem to have a brief issue. I'll back up to an older copy, which I know was working. Okay, so this one succeeded. So we've got our client and our server. Let's go to console app 55. And gRPC service 33. Okay, this time it's succeeded. I've got some beta preview bits on my computer, which might have interfered when I created that new project. So here we can see our gRPC console app. It successfully called our server. So we passed in .NET Conf and we got a message back, hello .NET Conf. And we can see on the server we received our gRPC call, which we can see here. So it came in as an HTTP2 call to localhost. This is a standard gRPC URL, application type gRPC, and our server processed it. So now that we've seen how to create our very first gRPC application, I want to do a deep dive on gRPC performance. So gRPC benefits from the performance improvements that have been made in HTTP2. And one of those performance improvements is more efficient use of TCP connections. So HTTP 1.1, typically whenever you make concurrent requests, each one of those is going across on its own TCP connection. HTTP2 adds the ability to do multiplexing. So multiplexing allows you to make multiple concurrent independent calls via one TCP connection. And a good way of looking at this and seeing it for yourself is within a browser, taking one image, splitting it up into 100 small images, and then attempting to download it using each protocol. Only a couple can be downloaded at a time via 1.1, while with HTTP2, all of them are downloaded at once, and it's much faster. Another key benefit of gRPC is its low network usage compared to REST. So it achieves this in a couple of ways. One is it uses HTTP2's binary framing and header compression. So HTTP2 is able to take headers, which it sees have been sent multiple times in a request and response, and rather than send them with every request and response, it just sends a couple of bits. So it's able to make some significant savings there to header size. The bigger contribution to low network usage is protobuf message serialization. So it's a contract-first binary format. So here we can see some JSON on the left and a protobuf contract on the right. Because both the client and the server have the protobuf contract, we don't need to repeat all this information with every single call. There's no point us sending query and saying query is a string, page number, results per page. Both sides already know this information. So having the contract on both sides allows us to remove unnecessary information and just focus on the actual data itself. So although these two bits of text look about the same size, the actual content that's getting sent with protobuf is just very small binary. Someone in the community measured the difference between JSON and protobuf, and at least in their case, they found that protobuf was between a quarter or a third the size of JSON. Now, your mileage may vary. It will depend upon what data you're sending, but generally protobuf should always be smaller. So I've talked about why gRPC should be fast in theory. Let's look at some real-world numbers of gRPC versus RESTful APIs, in this case, comparing against MVC. Now, with both MVC and gRPC using HTTP2, just for consistency, I observed gRPC was 25% faster. And if we use a advanced gRPC technique called bidirectional streaming, it is 140% faster. So streaming with gRPC is when you're able to establish a single request and then simply stream data backwards and forwards. So you eliminate the overhead of creating a new HTTP request every time you want to talk to the server and having the server parse that incoming HTTP request. You're just dealing with the gRPC message data. Now, this doesn't work with every scenario, but if you really care about performance to the extreme, it's something you might want to explore when you're using gRPC. Let's look at gRPC versus some other implementations. So we found with measuring gRPC on .NET 5, it either equaled or exceeded Golang. Also in this graph, we can see gRPC.core. So gRPC.core is a slightly older implementation of gRPC for .NET. So the way it works is it wraps a native C++ implementation. And probably why it's slower is it has the overhead of both that .NET code and then the C++ implementation, while gRPC ASP.NET Core is fully managed. These numbers, we can see we're getting 600,000 requests per second under heavy load on one machine. These are using traditional unary calls, so that's a traditional request and response with gRPC. If we explore using that bidirectional streaming to eliminate some of that overhead, we can get over 1.5 million requests per second, which is pretty impressive for a single machine. Although that machine has pretty good specifications. So finally, let's look at what work went into gRPC to get these good numbers in .NET 5. So the biggest improvements came from optimizing HTTP2 and HTTP client and Kestrel. So that's stuff like reducing latency, removing allocations, improving concurrency. These improvements are great because they benefit everyone who is using HTTP2 in .NET, not just gRPC. Kestrel now fully supports HPAC compression. So it supports taking large response headers, and if they're repeated multiple times, compressing them down to just a couple of bits. That just saves on network usage. The .NET client, HTTP client, and Kestrel now support keep alive pings. So keep alive pings are a technique for keeping a connection warm. So perhaps you might have an application which doesn't have much usage over an hour, and any TCP connections are closed. As soon as you make a call, you have the overhead of creating a TCP connection, doing a TLS handshake, establishing an HTTP2 connection, and finally actually making your call. Keep alive pings can be used to keep connections alive and warm so that when you want to make a call, they're ready to go. We're working with the protobuf project to support span. So when protobuf serializer supports span, we'll be able to eliminate the need to allocate byte buffers when serializing and deserializing protobuf. And finally, we're adding support for additional transports. So gRPC should be able to be used over named pipes and Unix domain sockets when you're doing inter-process communication on a local machine. This offers performance benefits over using traditional TCP. And that's all I have for you. This is a very brief introduction to gRPC. I have documentation available if you follow this link. I hope everyone gives gRPC a try. It's very easy to get started, and it offers great performance improvements and many other improvements I haven't talked about. So hopefully I've got some time available to answer some questions.
Yes, James, you do. We actually have one question. Let me share that screen in a second. And actually, it's a pretty big one, is which ways of authentication does gRPC support?
So gRPC, it uses standard HTTP. And because it does that, and because our implementation of gRPC integrates with ASP.NET Core, you can use pretty much all standard existing authentication mechanisms when you're using gRPC. So some examples are you could use JOT tokens, you could use client certificates, so that's mutual TLS authentication. The one exception to authentication that you can't use with gRPC is you can't use Windows authentication. Windows authentication is limited to HTTP 1.1, and because gRPC is 2 or above, you're not able to use that as an option.
Well, that's great. So essentially, any middleware that I may have right now as part of my ASP.NET Core application, whether it be custom or something out of the box, would just work right on top of gRPC.
I think so. I think I would assume it does. Like obviously test it, but
Yes.
I think yeah, because gRPC, it's although I talk about binary this and like huge efficiency gains, like it's still just running on HTTP 2, which is very similar to HTTP 1.1. Like there's still headers. Like if you've got an authorized header and you're passing it along, any existing middleware will use it. And because we integrate well with the ASP.NET ecosystem, yeah, your existing middleware should just work.
Sure. Actually, I have a question. We can make it brief here. Is that from like a load balancer perspective, right? So I have my applications behind the scenes. Would I run into any issues with using gRPC, or because it's using HTTP2, it should just forward those across?
There is actually one interesting issue with gRPC and load balancers. So I talked about multiplexing before
Yes.
and how you can like just have a single TCP connection and all your requests will go via it.
Mm-hmm.
Load balancers, especially like low-level load balancers, the way they work is they'll get an incoming TCP connection, they'll forward that to one computer, they'll get another TCP connection, they'll forward it to another. If all your requests are going via one TCP connection, all your load will go to one computer. So like there's the idea
Right.
of level 4 load balancers, which work at that level, and then level 7 load balancers, which work at a higher level and are able to support sending individual streams, so individual requests over HTTP2 to different computers. So if you're using something like gRPC, you might want to use something like Envoy or perhaps YARP to take you would make calls to that proxy load balancer, and then it would be responsible for sending requests to different computers.
Yeah, so that way you can sort of fan out those requests and actually get the best performance out of the scalability that you've built in.
Exactly.
Perfect, great. Well, I don't see any more questions that we have. James, thank you so much for taking the time to talk to us.
Thank you.
I'm really looking forward to playing more with the gRPC bits and .NET. And for those of you watching the stream, we are actually going to kick off right next to a video. Our next speaker, Jessica Dean, couldn't make it because of vacation and other and other things that got in the way. So we got her talking about DevOps, waffles, and superheroes. So Jessica Dean's video is coming right up.